This video demonstrates how to conduct the material nonlinear analysis or the plasticity analysis or the spring back effect analysis using ANSYS Workbench. You can observe here there are two bodies. The first body is the platen body, which is going to compress the less stiffer bush. The platen is made up of high stiffness material and is allowed to displace in the Z direction. When we observe carefully, the platen is going to displace the bush for a distance of 5 millimeters and it is retrieved back. But the bush is going to retain in the deformed state itself and failed to regain its original shape, size and dimension. This behavior is due to its nonlinear material properties. This video or this tutorial will take you through the different steps involved in conducting the material nonlinear analysis. We are going to conduct a linear analysis first, understand the behavior, then we are going to conduct the material nonlinear analysis and understand the difference. In the real world, no material will exhibit the linear behavior. All the materials are nonlinear. But since it is a very difficult or time-consuming process to obtain the nonlinear material properties for a particular material, we assume that material to be linear. Let us proceed with the tutorial. Create a new static structural analysis file. Rename the file with the name Plasticity. Right now, we are interested in the linear analysis, later nonlinear analysis. Hence, enter the name as linear. 01. Geometry need to be imported. The geometry need to be imported. Before that, let us define the materials. Double-click on the engineering data. You can observe that the structural steel material is the default material. Let us increase its elastic modulus so that this material becomes very, very stiff. In terms of MPa, let us increase its value. Enter. Similarly, define a less stiffer material by visiting to the engineering data source. Under the general materials, locate the plastic material or the polyethylene material. Polyethylene material is now included. Pick on Return to Project. Now, pick on the geometry, right-click on the geometry, pick on Import Geometry. The plate and the bush step assembly is available in the temporary memory. Let me import the same CAD geometry. You can observe a tick mark which says the geometry is successfully loaded. At this point of time, the engineering data, which means the material property, currently linear, and the geometry are loaded. Right-click on the model. Before that, we want to do some modifications in the geometry. Hence, right-click on the geometry, pick on Edit Geometry. The Design Modeler window is now opening. At the left bottom corner, you can observe the status of opening. Under the ANSYS Workbench window, ensure the unit as millimeter. Pick on OK. You can observe the geometry is being loaded but is not yet imported. Under the Operations in the Details view, pick on Add Frozen, which means both the bodies will not merge with each other. Two bodies will be treated independently. Now pick on Generate. Observe the CAD geometry is now imported. Let us observe very closely. Right-click, pick on the View, Right View. You can find a gap which is existing. This gap was purposely maintained to avoid the merging of two bodies when it was modeled in a single part file using a CAD modeling software. Let us translate the platen body or the plate body in the negative z-axis by 1 millimeter, because the gap which is existing over here is 1 millimeter. Pick on Create. Select Body Operations. We want to translate the body. That body should be this body. Select the body, pick on Apply to confirm the selection. The type of operation that need to be performed is Translate. Hence, select the Translate from this pull-down. We need to translate in a particular direction. The direction need to be defined by the coordinate system. The component of the coordinate system in which the body need to be translated is z-axis. -1 has translated the body. You can observe here, but it is not yet generated. Pick on Generate. Observe the gap is now closed. This geometry is now ready to be exported to the ANSYS Mechanical or for the solution purpose. Visit to the project page. Under the model, right-click, pick on Edit. This is going to open the starting mechanical, which means the mechanical window is now opening. The attach status is completed. Some of the windows are missing from this graphics area. Hence, let us reset the windows. Pick on the View, pick on Windows, pick on Reset Layout. Now we can observe the graphics, the project tree, and the model details. As we discussed earlier, these two bodies are made up of two different materials. The platen is made up of high strength steel and this body is made up of less stiff plastic material. Pick on the geometry. Under the geometry, there are two parts. The first part need to be assigned with a material called as polyethylene. The second material or the second body is taken by default as a structural steel. Let us come to the contacts. Under the contacts, there is one contact which is being identified automatically, and the type of the contact is bonded. We don't wish or we don't want to keep this contact as bonded, hence change this type to be frictionless contact. Under the behavior, change the behavior to be asymmetric. Under the formulation, select it as augmented Lagrange formulation. Let me drag this window for the clear visibility of the contact settings, which will be done. Under the detection method, use node normal to target. The normal stiffness need to be controlled manually. Enter the normal stiffness value to be 0.1. Update the stiffness of the contact for each iteration. The pinball region, let us keep it as program controlled. Once the necessary contact settings are done, let us proceed for meshing the bodies. Pick on the mesh, right click, pick on Generate Mesh. The mesh is being generated. Observe that the mesh is not mapped properly at some areas, hence we can find the penta elements. Now, let us proceed for defining the mapped face meshing. Right-click on the mesh, pick on Insert, pick on the mapped face meshing. Right-click on the screen, pick on Select All, which is going to select all the faces because the face is highlighted here. All the faces have got selected. Pick on Apply. Observe the mesh has got disturbed. Right-click on the mesh, pick on Generate Mesh. This is going to give us a systematic mapped mesh. Observe the mesh is mapped compared to the earlier mesh. Let us define the analysis settings. Observe and understand the steps very carefully. We are going to fix this end. And we are going to apply the displacement on the platen, which is going to compress the body because we have restricted it here. And then we are going to take the platen back and study what is going to happen on this bush. Which means we are going to define or we are going to solve this problem in different steps or multiple steps. Enter the analysis settings. Use the number of steps as 3 steps. Right-click on the static structure, pick on Insert, pick on the fixed support. Pick on this face, pick on Apply. This face is rigidly fixed and the other face is free to be compressed. Right-click on the static structural, pick on Insert, pick on the Displacement. Displacement need to be applied on this face, and this face with respect to the global coordinate system has to move in the negative direction. Pick on Apply. Under the definition, pick on the x component to be 0, that is constant, y component to be constant, the z component need to be moved by -phi. Once we enter the displacement, You can observe this in a tabular data because we are defining this problem in 3 different load steps. In the first load step, we don't want to displace this platen. Hence, we'll keep the displacement as 0. In the second load case, we will displace it by minus 5 millimeters. And in the third load case, we are going to retrieve the plate back. That's the reason why you can find the graph of the displacement. In the first load case, there is no displacement applied on the platen, hence it is 0. In the second load step, that is from 1 to 2, the displacement on the platen is from 0 to minus 5 millimeters in the z direction. In the load step 3, that is from 2 to 3, the platen is going to be retrieved back in the z direction, that is, taking it back to the initial position, that is 0. Let us make some analysis settings now. The current number of step or the current step number is 1 since there is no load or the boundary condition, since there is no load or the displacement in the first load case. Let us use the automatic time stepping as program controlled. Under the second load case, the time stepping should be given for the smooth convergence. Under the initial steps, enter 30. Under the minimum steps, enter 20. Under the maximum steps, enter 50. Same thing has to be carry forwarded for the step number 3. Hence, enter the current step to be 3. Automatic time stepping should be on. It should be defined with the initial steps of 30, minimum to be 20, and maximum to be 50. Once the analysis settings has been defined, let us proceed for solution of the problem. Right-click on the solution, pick on Solve. Pick on the solution information. Observe the solver output or the convergence graph. You can observe the blue colored line in the graph says the first load step has been converged. These are the sub-steps in the second load steps which are now converging. You can observe the status of the solution. Second load step is about to complete and it is completed. Now we are in the third load step. The solution is in process for the third load case. The substeps are converging faster. The third load step has been converged and the solution is completed. Let us post-process the results of displacement. Right-click on the solution, pick on Insert, pick on the Deformation, pick on the Total Deformation. Right-click, pick on Evaluate all the results. You can animate this with a scale 1:1. Animate the result that the body is compressed and decompressed. And there is no permanent deformation observed. This is because we have not included any non-linear material properties into the model. Then let us retrieve what is the displacement versus force reaction graph. Pick on the solution, pick on the Insert, select your user-defined result. Under the expression for the body, that is this body, select the body icon here to select this body Pick on apply. The expression for this to be absolute. Displacement Z. Enter. Similarly, right-click on the solution, insert, pick on the user-defined result. Similarly, under the expression, pick on absolute FZ. Now we have defined two expressions to plot the graph for the deformation versus the reaction force. Let us rename this user-defined result as UZ, displacement Z, and the second user-defined result as FZ, that is reaction force Z. Using these two user-defined results, we want to plot the deflection versus the force graph. Use here chart or the table, new chart and table. It will include a chart here. We want to define two objects. The first one is displacement, press hold control. Next one is the force. Pick on apply. The x-axis has to be represented by the displacement, that is UZ max. And the plot style need to be with the points and lines, hence pick on both. The scale should be linear. You can label the x and y axis. Under the content, we are interested in the tabular data, chart data. Under the time, pick on omit the display of the time. Now evaluate all the results. These results will be now captured into the chart. Pick on the chart, make some necessary changes. The UZ minimum should be omitted. UZ max should be displayed. FZ minimum should be omitted. Now, let us pick on the graph. You can observe here the graph which is plotted for the displacement of approximately 5 millimeters. The reaction force started go on increasing. Let us switch on the animation plot for this so that the understanding will be clear. The graph for this displacement, switch on the graph. And pick on the chart now. As the displacement go on increasing, the reaction force also started increasing. And when the displacement started decreasing, the reaction force also started decreasing, following a linear path. I repeat what I'm trying to say, which means when the bush was compressed, the reaction force which was happening on the bush is same that of the case when we are retrieving the platen back or decompressing the bush, which means there is no permanent deformation or the spring back or the plasticity which was observed in this. Now, let us proceed for the nonlinear material analysis. Visit the project page. Duplicate the current static structural analysis file. Pick on duplicate. You can observe a copy of Plasticity linear is being created. Use here nonlinear. Pick on the engineering data. Under the polyethylene, select this material. Right-click on the multilinear isotropic. Pick on the include property. We are going to include the nonlinear property for this material now. The plastic strain initially is 0. Corresponding stress, let us say 18 for this particular material. And when the plastic strain was 0.123401, the stress has got increased to 38. And when it was 2e minus 5, say it was 39. And when it was 3e raised to minus 5, the stress was 40. And when it was 4e raised to minus 5, the stress was 41. Let us say this is going to be our non-linear material property data or the curve for the current analysis. To explain it a little bit clear, let me open the paint. You can observe normally a stress strain can be plotted either in this fashion or it can be either in this fashion for different materials. Till this limit, called as elastic limit, the property is already defined in the linear material property. The nonlinear zone has defined now, which means the data points associated to the nonlinear curve have been entered now. That's the reason the curve which you are going to find it in the project tree is only the plastic deformation zone, that is only this zone, because the zone below the plasticity zone is already captured in the linear material properties. Having understood this, let us proceed for the analysis of the nonlinear material. Pick on Return to Project. Double-click on the solution. ANSYS Workbench information. Upstream data has been modified since it was last read. Would you like to read the upstream data? Pick on Yes. Whatever the material property changes we have made in the material properties, that has to be replicated in the new analysis. Pick on the View, Windows, pick on the Reset Layout. This is going to reset all the windows. We have not changed anything apart from the material, but the solution is disturbed because of the material property. Right click on the solution, pick on Solve. The solution status can be monitored using the solution information, either the force convergence or the solver output. You can observe we are in the second load step because it has crossed 1.67, 82% in second load step, 97% in second load step. Second load step is completed. Now we are into the third load step. %47% in the third load step, 62%, 82%. It's about to be finished. The solution is completed. All the load steps have been solved. Now you can observe very clearly that when we switch on the animation, it compresses the body and it comes back. The platen is going to compress the body and come back, but whereas the bush is going to remain in the deformed state itself. To animate it very smoothly, stop the animation. Use the number of frames as 100 and the time to be 10 seconds. Let me explain now. Clearly observe. In the first load step, no load. Second load step, the body is compressing. And third load step, the body is decompressed. And since the bush has got the permanent deformation, it cannot recover its original shape and size. It is permanently set. And when we look at the force and deflection curve for this behavior, we can observe clearly under the graph that it has not followed the same path which it has to follow in the linear analysis, which means as we go on increasing the displacement, the reaction force started increasing. And when we started unloading the plate, at that time, the deformation was not 100% recovered. Or to be more clear or to be more precise, you can observe the displacement was supposed to happen by 5 millimeters. Hence, as we started applying the load, the displacement, the reaction force started increasing and the displacement has stopped for 5 millimeters. When we started retrieving the platen back, the bush did not came back to its original state and it just came back only 2 millimeters. The 3 millimeters of permanent set you can observe in this graph. To summarize, we have discussed the geometry import, defining the linear material properties, understanding the material nonlinearity, understanding the spring back, and how to define the user-defined results and how to plot the chart. Thank you for watching this video. For more videos, please contact engineeringtutorsdesk@gmail.com, or you can visit my site engineeringtutorsdesk@gmail.com is my mail ID. sites.google.com/site/FEA engineering design is my website. Thank you for watching this video. If you like this video, please click on the like button. If you're interested in the more videos, click on the subscribe button just below this video.